one? I just randomly select one. I mean, yeah, it's pink.
All the
Oh, I see. Oh, it's cassettes.
Yeah.
I was trying to match the pattern.
Cassette war.
Okay. It's good to see you guys. What's up? I got that few graphs, but I got them just at the beginning of my 2 o'clock call. So I haven't been able to look at them yet. Oh, hi, Ying Ying.
Hi, Rich. Hi, Hua.
Hi, Professor.
Hi.
Yeah.
I was just saying, I got those slides, but they were just at the beginning of my last call, so I haven't had a chance to look at them yet.
Yeah, that's fine. That's fine. Yeah, Bing will go over the slides. Yeah.
Okay, that sounds good. I can handle that. Let me move that over to the other side.
Okay. Okay, now I'm.
Your headset it's very unique.
Well, it's actually very comfortable. My kids are all gamers and work for Google and stuff like that, so they have their opinions on what pieces of hardware work and are comfortable, and this seems to work and is comfortable. I'll take their advice.
Yeah, looks very cool.
Yes.
Yeah, well, it actually has flashing LEDs if you turn them on, but that's not my style. That's definitely not my style.
Kind of with the content we are saying.
But it works well. I can't complain. So tell me what's up.
Yeah, we are working on RFID related projects that we want to use the RFID to help us to. We envision that we can attach it to humans' clothes eventually, so it's like a part of smart clothes. So and then it's going to be attached to the chest area or abdominal area, so that it can pick up people's heartbeats and movement caused by breathing.
Right.
So in one project, we like to utilize it for the well-being monitoring, to measure both during the daytime and at night, what is the breathing rate and heartbeat. And the other is that because supposedly each person has a very unique breathing and heartbeat, either combination or separately. So we also like to use it as authenticate the users eventually.
Right. Are you talking about 2.4 gigahertz tags?
Yeah, I think we're using 2.4 gigahertz tags. Yeah. It has the example of the tags. Do you want to show it to Rich? You have it at home, right?
Yes.
Okay.
Yes.
And you also are evaluating the presence of the conducting body. People's bodies affect the tags dramatically.
Right. Yeah, that's the hard part. So currently, when we do the experiments, so we actually encounter difficulties. Yeah. So I think that you are actually very familiar with RFID. And so we'd like to ask for your opinion about that.
Right. I have this wonderful view graph from Walmart 10 or 15 years ago, the first time they tried to force their vendors to use RFID. And I went to a talk by the CIO of Walmart many years ago, and she was saying that they got it to work in their own factories with their own equipment under strict control, and they were very happy to get 80% accuracy. Now, you know what Walmart's profit margin is. If they lose 20% of their stuff, that's not a business model they can live with.
Yeah.
So these passive tags have real limitations that you have to work your way around. And being next to a conducting body is one of them.
Yeah.
Right.
Yeah, exactly.
And the other one is all the multi-path issues, because the guys that I just saw Ben flash the tags up a minute ago. One of the guys that makes those Alienware, makes those tags, we went to a booth of theirs once, and he was describing how good the tag was, and he was waving it around. What he didn't notice was his reader had a light on it whenever it connected. And as he was waving it around, less than a meter from the reader, it was turning on and off depending upon his orientation. There's a piece of physics that says the tags absolutely have to have a direction where they don't work at all. Right, that's the combing the hair on the billiard ball problem. So there has to be one direction where they never work at all. And since they're paired devices, you're guaranteed to have an orientation, a reasonable fraction of orientations where they just don't work. And there's nothing you can do about it. Other than rearrange, rather than move the tag or move the transmitter. And they're not even set up to have multiple transmitters, so that makes that a little bit difficult.
Okay.
So that was a cord dump. I interrupted. You were trying to explain to me what you're hoping to do. I saw the paper about faces. Yeah. I saw the paper about faces. That was a different interesting approach altogether.
Right. That is something I come across, and that is also related. Yeah.
Have you seen the work that Xiaoran did with the headsets? Okay, Xiaoran in the lab. He's now.
I know Xiaoran. Yeah. I haven't seen that before.
What he did was he used an over-the-ear headset like this, and then he used the speaker in that, and put a chirp sound into that speaker, and the structure of your outer ear here generated interference patterns with the sound coming back, and it changed the impedance of the headset, so you could measure the interference pattern, the speckle pattern that came from the folds in the ear, and accurately identify whose ear it was on.
Yeah,
right? Because right, and he can give you that paper. I can give you that paper. It's in preprint right now at Mobicom. So that process was done acoustically, so it's really cheap to do, and it's very low speed. You can use a simple microcontroller to do all the processing, and he was able to identify that. So it seems to me that if you did that to somebody's face, sound, because it's dirt cheap and really slow, so you can use any kind of processor on it, a $5 processor, you're done. You can get a pattern that has to do with the position of your face and the reflectivity of your face, but do it with sound. And it's much, much, much easier than doing it with radio.
Oh, okay. And
much cheaper. Much cheaper than doing it with radio.
Right.
I just mentioned that if you hadn't thought about it. I mean, as a group, you like to operate sort of the next level up where there's a commercial piece of hardware that you're readapting.
Right.
And that's certainly an easy way to do it, but I'm just pointing out that the fact that RFIDs are not ubiquitous is because of their limitations. If you can design your system around those limitations, which you probably can for the heartbeat, but you just realize that with somebody sleeping, some fraction of the time you won't be able to get a heartbeat from them because they'll be in the wrong orientation.
I see. Okay.
And you may, if you had a second receiver and paired it up with them, you could solve that problem, but the receivers themselves are expensive. Right?
How much could that be solved by using multiple RFID tags with different orientation?
Yes, you could do that. That because you've got the space on the body, you could do that. But you'd have to engineer that. And the trouble is when you put it on the body, it's hard to get a different orientation. I mean, you could go 90 degrees, but if you're in a node, you have to be a quarter wavelength away to solve that problem. And you also have the conductivity problem of the chest to deal with, which makes the signal much weaker and means you won't see any of the signal on the other side of the person. Right? You only see it will completely shield the signal coming from the other direction. Right? I assume you've seen that or something like that. Yeah.
Yeah, I think the problem for the acoustic sensing is that we had experience before, but the acoustic signal actually attenuated quickly. It couldn't sense do the sensing from distance.
Depends. If you want to do a face, you're not doing the face from a distance with RFID's got a range of a meter. Right? You're not going to get a distance with RFID. You'd have to have millimeter wave. You'd have to have a millimeter wave array to get some structure at a distance. But you're lucky if you get a meter on RFID.
I see.
And on top of the body and a conducting body and
I don't know. What's your experience been? Have you been played with it?
Yeah.
I mean, they promise lots of things, but I've never seen them deliver.
Yeah, you mean for the RFID?
Yeah, for the RFID. I mean, they'll promise you a couple of meters.
You can you show us your setup?
Yeah, some of the results maybe. Yeah.
Sure, I'd love to see that.
And Bing, I asked you to bring your RFIDs. Yeah, once you bring, you can show it.
Yeah, he waved one up. I saw.
So
Yeah,
this
those
is,
are
can you see
the
here?
standard UHF RFID.
Yeah, this is everybody tag.
Who are those made by?
Who are
those are made by? Who makes those?
Who made those?
Oh, it's the how to pronounce this? Is the
Don't worry about it. What do they claim the range is? What do they claim the range is?
Yeah,
That's okay.
Sorry.
What do they claim is the range? What do they claim is the range with their reader?
The range? The range is...
The range, how, yeah.
Yeah, the reader is around the large range is around 20 meters.
20 meters?
Yeah, 20 meters.
Have you tried them?
No, we just tried around 1 meters to 3 meters. This
Do they work reliably at 3 meters? Do they work?
In my home, 1 to 3 meters.
Right, reliably. So if you put them in 10 different positions and try to read them, it works every time?
Yes, every time.
At 3 meters?
Yeah.
Okay, probably not at 20.
So
how much power is the transmitter?
Okay, so
4 watts?
Let me check. Yeah, maybe. Let me check this.
Usually they're like, I think the maximum in the U.S. is like 4 watts.
Yes, for the because the U.S. have the FCC regulations.
Yes.
So, yes, they have the regulations to let these manufacturers that the max watts is 4, like you said.
Right.
Yeah.
Okay, I'll point out that it's different in Europe.
Yeah, different in Europe and China and other locations.
It's lower in these other places, and those rules are evolving. So to get range with the passive RFIDs, you've got to blast it with the maximum currently allowed power. And you're putting it on a person, and you're having trouble connecting with it. So that means you're hitting the person with the maximum allowed power.
Oh.
I don't expect that's going to remain that way indefinitely. It's a high exposure, and depending upon who's running what politically, that could end up getting changed.
Okay.
Right. I mean, I wouldn't want to expose my kids. I wouldn't want to expose my kids to that.
Yeah.
There's enough uncertainty about what's going on to be able to do that. That's a significant amount of power. Not enough to cook anything, but certainly enough to make you worried if you don't understand what's going on. And I'm happy to share, I've got a whole dossier of stuff on RF safety it's a field in flux right now.
Okay.
And so that's one of the things that's worrisome about the passive RFIDs.
I see. So for Sharon's paper, you mentioned that he utilized the RFID, put it in the headphone, right? So
yes.
So the transmission also set 4 watts.
I'm sorry, you broke up.
So what is the transmission power? Is it also 4 watts?
No, it's not RF. It's ultrasound. It's very, very low. In fact, it's just acoustic. It's an acoustic chirp.
Oh.
So it's an acoustic chirp that goes whee like this, and each one of those wavelengths samples a different part of the ear and is in resonance with it. So it's a very low power sliding tone acoustically, and that gives you all the information you need about the shape of the ear to be able to uniquely identify the person.
I see. That's very interesting.
And that has no radiation limitations or anything that you have to worry about.
Yeah, about acoustic is there's no radiation.
Right. It's guaranteed safe.
Yeah.
Because that was actually not even ultrasound. It's just acoustic.
Sorry, I'll take a look.
Yeah, okay. It's just a thought, and you may not want to get into that, but
Yeah.
RFID's got its own problems. So anyway, why don't you tell me more about what you're doing and with the measurements you've
Can you
made?
share your screen? Bing, can you share your screen? You should go ahead and do the presentation.
Okay.
Okay.
So we
Good.
can go along with your slides, right? So you at least you show something. We can talk about it.
Okay. Can you see my screen now?
Yes, I can.
Okay. So yes, I'm going to briefly introduce our project and what we are doing now. Okay, in this slide, page 2 shows our background and the application scenario. So we plan to use the HRV as a matrix to measure the interbit intervals. Yes, and why we use the HRV? Because HRV is very important for the human. It can be as a unique biometrics for everyone. So also it's considered as an essential indicator, reflect the health of our people. So we plan to use this, and also the below two figure shows the application scenario for the security domain. So we can use it as a footprint to authenticate the user. So this first slide. Second one is the objective of our project.
By the way, Ying, maybe I'm cynical, but the heart rate variability tied to your screen is a perfect thing for an advertiser. They'll be able to tell what your response to various stimuli are directly.
You're right. Yeah.
Yeah, okay. Anyway, go ahead, Ben. Sorry to interrupt.
Anything that you can use for authentication, I think it's private, right? And so
yeah, but you have
very sensitive
right, and we all know how well and how private authentication is. Almost nobody ever breaks into another system anymore, right?
Right.
That's a joke. Okay, continue, Ben. I'm sorry.
It's fine. And objective is first things we need to extract fine-grained interbit intervals from the RF signals.
Right.
Yeah, mixed with the heartbeat, signal respiration, and ambient noise and multipass signals. And then we explore use appropriate HRV matrix to measure this extracted IBI. But also we need to provide that our approach should be a contactless interaction approach and also a non-intrusive approach. So this is like the Professor Chen said, smart close. So this is objective. And the next slide shows the hardware we utilize. We have now. The first one is the RFID reader and the antenna and the tags. So the reader now for the US regulation, it has the frequency hopping. So we have the 50 channels.
Oh, good. Yeah, that helps with the reliability.
Yes, and also we have the antenna and RFID tags. We also use the monitor, ECG monitor, to collect the heartbeat signal from our body directly as a reference. So here shows our equipment now. Next slide shows the experimental setup. We conduct some preliminary experiment. Now the distance between the antenna and the body is around 120 kilometers, and we test the sitting and standing. And now we attach our tag on chest and abdomen, and we collect around 30-second signals. And the reader mode for this reader is use the max throughput. The sampling rate for single one, if we only use one tag, is around 220 Hertz. And if we use 5 tags, the overall sampling rate is around 720 Hertz. But for each tag, it's similar, 100.
I want you to go back a little bit for me. And are you measuring the Doppler shift from the tag? What is the actual measurement you're making? How are you making the ECG measurement?
Well, ECG measurement.
Yeah, I mean, you're using the tag. I'm a little confused on how you're using the tag to do the measurement.
So,
You didn't put in a method here.
Monitoring is just for this ground truth measurement.
Ground.
Okay.
Right.
Yeah.
And currently he's trying to pick up the RFID readings. And for the RFID readings, I asked him to do two kinds of testing. One is that try to measure the breathing rate that is causing his chest movement. So I asked him to do, for example, to do deep breath, for example, for every second.
I'm sorry to be simple-minded, but I'm just trying to understand from the way I look at the world, what is it you're measuring about the tag? Are you measuring the phase shift, the frequency shift? What is it that's changing when the chest moves?
Professor.
Phase shift, right? He's
You're looking
measuring
at the phase.
Phase.
Okay, the reader gives you out phase information.
Yes. The phase and RSSI. Yes.
Okay, but the RSSI is not as useful, but it gives you actually the carrier phrase.
Yes, phase.
Okay, good. That's what I wanted to understand. You're using that carrier phase to do a Doppler shift, basically.
Yes.
Or not quite a Doppler shift. You're moving the position. You're not doing it.
Just the phase difference.
Just the phase difference from moving it. You're doing interference measurement. You're holding, the wave comes in, goes back out again. When you move the chest a little bit, the phase changes a little bit because the reflector has moved a bit. Okay, good. Thank you. I just want to be sure I was. And the ECG is just your ground truth.
Yeah, as a ground.
Right.
Okay. Okay, good. Thank you. Continue.
Okay, so this is the experimental setup. Okay, next slide shows our results now. So now we have the first things we need to do the phase calibration. So
Please tell me what the axes on this are. They're too small to read. I can't read the vertical axis.
I cannot.
The vertical is the phase, and the frequency on the right is phase. The left is frequency.
Yeah.
Okay.
The frequency. Yeah. So.
The x-axis are the time and basically
Yes.
sample index.
Yes.
Okay.
Timestamp in the horizontal axis.
Okay, good.
Okay. The first figure left above figure is the frequency change in the 50 channels. The right above is the raw phase, and the below two is the after the phase calibration. The first, the left below is we experiment with breath. Yes, we have the breath, deep breath.
Deep breath. So you need to tell us what do you do when you do this? When you collect this data, what do you do? Is it like every second you have a breathe? You breathe once every second?
Yes, 1 second, deep breath.
Deep breath. Okay.
Yes.
Okay.
And the right below figure is without breath, we just hold. Yes, around. Yes, so this shows now the raw data after the phase calibration.
Nice.
So that's good. I think for the left bottom, actually, you show for the deep breath, you show the periodic peaks, right? So I hope you can mark this, right?
Okay.
The phase calibration, right, with breath on the so you know that the x-axis numbers, right, x, right, and you know your sample rate. So actually, you can mark every second onto it, right? Vertically, you can have your vertical line to mark your 1 second time frame.
Okay.
Time interval.
Okay.
So you can mark it.
Okay.
Yeah, this is good.
Yeah, so I think
You've got lots of signal and noise there. That
Yeah,
looks excellent.
breathing.
What was the range here? Was it about a meter?
It's 1.2 meter.
1.2 meters.
1.2.
Okay.
Yes.
Okay. You can see because it goes as R squared, you're not going to get 20 meters out of this.
Yeah.
Yes.
Right.
Yes.
Yes.
I mean, you double that, you're going to get 4 times the noise.
Oh, 4 times noise. Yes.
Right. At least. So, okay, but that's a nice signal at a meter.
So
that's a good use case.
Oh, okay. So with the range this increase, that the noise may be increased significantly.
The signal goes down, but the noise stays the same.
Okay.
Right.
Yeah.
So you're going to, your signal noise is very good now. It gets to be hard. And what that really means is that you can find it. You can do like Xiaoran did with his mechanical measurement of heartbeat. You know about Xiaoran's work, Ying? He did the mechanic. Xiaoran Ji did the bed moving.
Yeah, bed moving. Yes, yeah.
Right, and to do that, you can do a Fourier transform, look at the data, and get a heartbeat out of that. But that's an average heartbeat. If you want the inter-heartbeat, you need very good signal noise on each pulse, right, to make that work. So that's why I was asking about the noise.
Right.
Right. You can get a heartbeat at a much lower rate, at a much worse signal noise. But if you actually want to get the actual, if you look at these right here, if you were to pick an inter-peak distance, I would guess your error is probably 10%, because it's hard to tell where the peak is.
Right. From the one that he wants to measure the heartbeat, it's hard. It's actually noise on the same level as the real signal, right?
Well, it'll be worse for a heartbeat because the chest won't move as much.
Right.
So the signal noise ratio is going to be much worse, I would predict, with the heartbeat, because if you think about it, if you look at somebody's chest, you can see it rise and fall when they breathe, but it's very hard to see their heart beating. Right.
Yeah, exactly.
Right.
So the figure on the lower right corner actually
Yes.
supposed to be the heartbeat, right?
Heartbeat, right.
He's holding the breath, removing the interference from the breathing. So supposedly there should be only the heartbeat there.
You should try an autocorrelation on the signal from around 3,000 out and see if you end up with a predominant frequency.
Mm-hmm. Yeah.
Whether you can pull the heartbeat out of there. You should be able to.
If he does the Fourier transform, I think for the heartbeat, we previously, we have a paper for vital signs model. I ask you to look, right? In order to look at the heartbeat, we convert. At that time, we convert CSI signals into the frequency domain.
Right. It's a little tricky because the actual heartbeat is at a low frequency, but the repetitive part of the heartbeat is at a high frequency. The rising edge at each one of the QRS complexes, you get a spike. So a simple Fourier transform isn't as useful as an autocorrelation, which will see if there's a shape of signal that repeats every 1/80th of a second. Right?
Yeah. So my question is, if he's going to do autocorrelation, right? Because right now the signal mixing with noise is so much, right? Mixing with noise. Actually, it's hard for him to do autocorrelation, right?
If you just slide along that signal and look for repetitive signal, that's what autocorrelation will give you.
Okay,
right?
But also in the frequency domain, right?
In you can get it in this domain, not in the frequency domain, but in the time domain. If you do an autocorrelation, which has got an offset to it, it just says that if I take the signal, chop it up into 10-second pieces and lay them on top of each other, what does that offset have to be before you get a big spike?
Yeah.
Right.
That
will give you
signals.
So,
You're right.
So for the autocorrelation, when he do this, is that going to be like sliding window or not windows?
You slide the window back and forth until the spikes line up on top of each other. You're assuming you have like 10 spikes that are similar and they're buried in noise. If you slide each one of the windows by 1/10 of the inner spike spacing, you'll get them to add up as linearly, and then the noise adds up as quadrature, and you can get the spike out from that.
Okay. So he can give it a try.
Yeah, I know from what Xiaoran was doing that they was able to get from this kind of quality of data, you were able to get the spikes out of it. Because you're essentially seeing a harmonic. You can't really, in the Fourier transform, it's very hard to see 80 beats per minute
Right.
That's down in the noise. That's down in the 1/f noise of the transform. But the fact that each one of those beats has a spike to it at a high frequency that repeats, that you can find.
Yes.
Right. Even though it's not a big component of the Fourier transform, it is a big component of the correlation.
Right. I think this is a very good suggestion. Very good suggestion.
Okay.
Yeah. I think he can also read the paper that Xiaoran, you're talking about the sleep monitoring paper, right? Xiaoran had with Yan before for the bed. Right.
Yeah, one of the bed papers.
Okay.
Where he's doing the ballistic cardiography. The reason I'm wandering off in this direction is because you started this with wanting to do the inter-heartbeat variability. To do that requires really good signal to noise.
Right.
Because you have to be able to get the inter-heartbeat interval, so you have to have a really good, signal to noise has got to be 10-to-1 or 50-to-1 in order to get any accuracy on your inter-heartbeat interval. And that is one of the things we learned, is that's one of the diagnostic tools you want, is the heartbeat varies a lot. And if you want to keep track of that variation for clinical reasons, you have to have a good signal to noise. Right? You can't do the autocorrelation and somehow you've got to get something that is happening that has a good signal to noise. Right? And EKG does. Right? And I will point out that echocardiogram does also. Right? And that's an ultrasound technique they use for judging heart rate. But that's that's not invasive, but you got to put something on. You got to put a powered thing on a person. It's an ultrasound measurement, right? The echocardiography, but it's considered the gold standard for understanding what's going on in the heart. It would be really nice if you could get that kind of information out of something like this.
Yeah. If we can get that out of something like this,
that's our goal.
Okay, now one possibility, if cost is not an issue, one possibility is to have multiple tags next to each other running at different frequencies from different readers. That gives you okay, imagine I have 4 tags, 4 readers, and they're always at a different frequency.
Oh, okay. So you're thinking about running at because currently
we have.
What's been tried is that he tried 2 or 3 tags, but with the same reader. So you're thinking that if we can increase the number of readers and the frequency, then that will help, right?
Imagine you have multiple tags with the same reader. The reader noise is going to be, you're going to have to slow down the sampling of the tags, and the reader noise is going to be the same. If you have different readers, the noise will be uncorrelated.
Okay.
So they add in quadrature, and you should be able to get a somewhat better signal to noise.
Okay.
Now, the readers are expensive, so that's not a practical solution, but that's a possibility.
Yeah, that's
and also
our research work. Yeah.
Right. I'll also point out that those RFID tags are resonant at 900 megahertz, right? They're tuned to 920 megahertz, the 920 megahertz rate.
Right.
If you put 2 of them together, and the tags are half wavelength tags, if you put 2 of them within a half wavelength of each other, they'll affect each other.
Yeah, they're resonant. You're right.
They're not independent if they're within a half wavelength.
Yeah.
So the trouble is, go ahead.
So the being he tried the distance in tags, right? Tried it. So we need to actually find that, right, about the wavelengths and also the resonance frequency.
Yeah, it's a problem because they affect each other and you don't get independent measurements. And the thing you need the most is signal to noise. Right.
Yeah.
By the way, I also haven't made the snide comment that if you're doing this with an American population that is not starving graduate students, most Americans are overweight, which means it's very hard to see the heartbeat from the outside. Graduate students are good because they're all starving, but once you get the real people outside world, there's actually I'm being a little bit flippant, but there's a serious issue with the population dynamics. The people that need this is Murphy's Law. The people that need this the most are most likely to have excess fat under their chest, right? So somebody who is thin and healthy and easy to see their heartbeat probably doesn't need a heartbeat monitor.
You're right.
I mean, I'm sorry, but it guarantees the people who need this are the ones that's going to be the hardest to make the measurement on.
Okay.
Right?
So I have another thought. Maybe that those antennas could be placed at a collar that's projecting. Backscattering the signals to the artery near your
Right. The carotid artery. Yeah.
Yeah, supposed to be the largest one, and also
That's why.
may have.
That's why in bad movies they always check your throat here to see if you're dead or not.
Yeah.
It's much easier than your heart.
Yeah.
That's a good idea. I have not seen people do that. There is a problem with the chin to clavicle distance is about the length of the RFID tag, so it would be very uncomfortable. Right? The chest is relatively flat, so or a section of a sphere for Americans, and it's easy to put the tag on it, but it would be very hard to get it here. It would be a very good idea if you had a higher frequency tag. Now, the work I sent you earlier from the guys 20 years ago, they were doing the backscatter directly off the heart, because at 2.4 gigahertz, the absorption length is about the distance the heart is below the surface, and you get a better signal that way than if you're looking at the tag, which is only looking at the surface of your chest moving. There's no penetration for the tag.
Right.
So but if you want to stay with commercial hardware, that's sort of what you're stuck with, right? Unless there's some way of amplifying it, and that's not obvious to me at the moment. I mean, that's why I would say there are various lower level strategies, like you could use ultrasound from the surface. You could use radio to launch an ultrasound wave from a tag that's on the person. That goes in, comes back out again. That's used for ocean scanning now, where you have a thing in the water that you hit with a radio pulse. It generates an acoustic pulse, comes back, and then sends a radio pulse back to the original transmitter. You can actually do that passively, convert it from radio to acoustics and then acoustic back to radio. But that's a different sensor. That's not a commercial item. But you do have the problem that the heart is so deep that it's hard to get that. On the other hand, the kind of techniques that Xiaoran did were easy to do with the heart because of the frequency, but they were hard to do with the breathing because it's so low frequency. Whereas it's easy to do the breathing. The breathing is a very clear signal, easy to see signal. So some kind of hybrid approach might be worth doing there. And certainly the breathing itself is worth knowing. And in my own opinion, I was on a National Research Council investigative committee once on IT for crisis management, for disaster management. And one of the problems is doing triage in big disasters. They take a football field, they lay it out with 1,000 people that have been injured, and you want to know which ones to treat first. If you had just a breathing monitor, because if the heart slows down, the breathing speeds up because of the oxygen reflex, right? So you have a proxy for the heart rate that is useful for triage that might not be useful for day-to-day diagnostics. But imagine you could slap one of these tags on everybody's chest and have readers that would reading them in groups of 10 or 100 people. Then you could actually do real-time triage, and the light would go on and say, this guy's failing, he's in cardiac arrest, or this person's got a congestive heart failure or something, and you can tell that just from the breathing.
Right. I think that's a very good idea. Yeah, if one is that you still continue to look into heartbeat, but as you pointed out, probably we can just focus on breathing, because the breathing pattern also shows whether the heart is functioning well.
Right. And if you're interested, if one of you send me a note after this call, I can send you a copy of that National Research Council report.
Yeah, I think that would be great. Yeah.
And it was basically done post-Hurricane Katrina, and a lot of it's interesting, the conclusion, this is not going to help you any, but I got to tell you the conclusion because I found it so fascinating. The conclusion was that the biggest thing that affected the effectiveness of the rescue workers was cultural, not technology. Yeah, the radios didn't work and the policemen couldn't talk to the firemen and so on. There were a lot of technological issues, but there was a cultural issue that overrode it all. No policeman wants to go into a difficult situation with a fireman behind him, and no fireman wants to go into a burning building with a cop as his only companion, because the policeman's not trained in that. So there are two different communities, tribes, that just won't talk to each other. And we talked to lots of first responders after that. But there are definite, triage is a really big issue for hurricanes and other natural disasters. And this would be fantastic. I often wondered whether you could do something like this.
Yeah.
And you guys have got, the technology's gotten far enough and cheap enough that you guys have got it to a point where you could imagine doing it as triage management, disaster management.
Exactly, disaster management or triage management. Right?
Yeah, that would be really, really interesting.
Yeah, also feels it will be a great visuals.
Okay. I don't want to play with the. You guys can't play with the tags. My brain always goes to playing with the tags. The way the tags do reflection is they short out or unshort out the antenna, right?
Mm-hmm.
That's how they work. They have a switch that turns the antenna. It shorts the antenna or unshorts the antenna. It changes the reflectivity of the antenna. If instead of an on-off switch or a 50 ohm and an open switch, which is what they actually have, you had a resistor there that changed resistance with temperature, you could easily change the amplitude of the reflected signal based on the body temperature.
Oh, really? Okay.
Right. You could, and to my knowledge, nobody has talked about doing that. You might be able to, and I believe that the resistors on that are chip resistors that can actually be changed. You'd have to talk to a vendor, get them under non-disclosure and talk to them. But if you put do you know how the passive tags work?
No.
Okay. You have a passive tag that is, you know what I mean by resonant?
Yeah.
If I use words that you don't know, please, I'm in a different community than you are, so please just let me know. If the antenna is resonant at 900 megahertz, and it has a 50 ohm resistor on it, so that all the resonant energy in it goes into that 50 ohm resistor.
Mm-hmm.
So if you hit it with a 900 megahertz radio signal, it will absorb that radio signal, but not send anything back. If you disconnect the 50 ohm resistor, now when the energy hits it, it rattles around in the antenna and gets sent back. So what they do is they connect and disconnect this resistor at the data rate of the tag, and they send a continuous signal in, and they disconnect and reconnect the antenna, and you get a beep 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 coming back to your reader. If the amplitude of that signal that comes back will be different if you put a 75 ohm resistor in there instead of a 50 ohm resistor. Some of it will come back, some of it won't. So there are resistors, there are components you can buy whose resistance changes exponentially with temperature, very fast with temperature. So over a narrow temperature range, you get a reasonable change in resistance. If you put one of those on the tag, then the amplitude of the signal coming back will depend upon the temperature of the tag, which if it's stuck to your chest will depend on the temperature of your chest. And if you put the tag on your chest and you put a layer of insulating foam over it so the heat doesn't get out, then the tag will go to your body temperature pretty accurately. If you leave it just on your chest, of course, it's got cold air on one side and warm body on the other, so you get something in between. But if you just put a thin layer of foam on it, like a Band-Aid, you'd be able to get the body temperature accurately and see that in RF. I don't think anybody's done that. That would be an interesting adjunct. So if you have the body temperature and the breathing rate, you would have a lot of diagnostic information.
Right.
That's very interesting. We will look into that.
Yeah.
Yeah. And a tag manufacturer may be able to do that, but...
So the resistor that you mentioned is we need to break the current antenna and change that resistor by ourselves, right?
Yes, you would, and that's not... People do that all the time in universities that are playing with that sort of thing. I believe, and I haven't seen the tags that Ben's got, but I believe that there's still discrete components, because it's very hard to make them as integrated components. I believe they're discrete components. If they're discrete, that's fine. If they're integrated, it's sort of okay too, because you can still put the other resistor in parallel across it, and you'll see a change with the change in temperature. Now, what I don't know is, can you get a thermistor in a small surface-mounted package that would fit on the tag? I don't know that. We can take a look. I would be surprised if you can't. Right.
Yeah, should be able to.
Anyway.
Good, yeah.
So anyway, I think you've got something here, Ying, that in the breathing that you could carry a long ways. I think the heartbeat's going to be really hard, because the chest just doesn't move. If you look at somebody's chest, you can see them breathe. You can't see the heart move.
Right.
Unless they're really skinny.
Yeah. So I'm thinking that probably we can just focus on breathing for now, and if we're going to do the heartbeat, I'm thinking that probably actually yes, is good instead of.
Well, if you're going to do the heartbeat here, I would say somebody should try doing the autocorrelation across this lower right-hand corner curve. If you can see the heart rate, the average heart rate over 50 beats is a good diagnostic temperature, is a good diagnostic tool for triage. It's not a good diagnostic tool for looking for abnormalities and subtle effects, subtle cardiovascular effects, like you were talking about in the first slide. But it's a really good tool for triage, because if you're bleeding out or you've got some kind of thrombosis or you're in shock, that'll change by a factor of 2. And you have good enough data. Looking at that curve, my guess is there's good enough data there. By the way, when you do this, I agree with Ying. The x-axis should be in seconds.
Yeah.
Right.
Yeah.
One of the problems with grad students is they forget that they're the expert, and they assume everybody else knows everything they do, which they usually don't.
Yeah.
So if you can do that, then if you had average heart rate and average breathing rate and the body temperature, you would have a spectacularly good triage tool. The other thing you'd like to have, which you can't get, is blood pressure, but the heart rate will be a proxy for that. A heart rate plus the breathing plus the temperature
Actually,
would give you enough information. I'm sorry, go ahead, Yang.
Actually, blood pressure can also be measured by the pulse intervals between two positions on the body.
Not if you have cardiovascular disease. If you've got partially blocked arteries or a stroke, there's an assumption you make when you make that statement, that all the arteries are clear and that the pressure wave is moving from one place to another. That is a healthy person. So you don't need to make that measurement on them. On a sick person, where you've got a stroke, a blood clot, partially occluded arteries, that person needs the measurement, and you can't do it that way.
Okay.
Right. So it's one of these things where the easy measurement to make, you don't have to make because the person's healthy.
Fair enough. Yeah.
Right.
Sometimes we do not know if the person is healthy or not, right? So it's like, you make this tool available to the general public, and then whether this person is healthy or not, hopefully it's like after such a period of monitoring.
I agree with you, except the fact that for the blood pressure, you have to make an assumption on the condition of their arteries.
But maybe not just a severe injured person or a severe sick person. I mean, just for somebody have a high pressure, maybe.
It depends on what the high pressure is from. If it's a renal hypertension, it has to do with the blood flow through the kidneys. It might have to do with blood flow through the peripheral. It might have to do with the heart volume being wrong. I mean, there are so many things that go on. You have to make an assumption to turn your pulse rate data into blood pressure data. And the assumptions are all lethal assumptions, so they're not ones you want to make easily.
Nice.
Right. So
you read
like that. Yeah, you'd like to have. I mean, if you want to get greedy, you want blood pressure and blood glucose, right? But that's very greedy for both of those. If you've got heart rate and breathing rate, you've got triage. You can save thousands of lives that way.
Yeah.
Out of the right condition.
We do one thing at a step, right? So if you can triage, I think that would already be very good. Then, when we have more experiences, we can move into like blood pressure measurement and also a glucose measurement.
Now, by the way, if you can fiddle with the resistor on the tag, skin resistance also tells you something.
Right.
Skin moisture, and skin salinity.
Yeah.
Right? So those tell you something. You could get those back from amplitude from a reflective tag, from the RSSI on a reflective tag, if you can change the resistor on the shorting element of the tag.
Yeah.
So that's just another thought.
And Tianming can also look into it, whether you can change the resistor. Yeah, can like adjust the resistor.
Right.
Oh, sure, Professor. Yeah.
I think that's a very interesting part. I don't see other people did that before.
I have not seen that. And of course, a measurement of the resistance of the skin could be made the same way, with the resistor replaced by 2 electrodes.
Right.
But they have to be close together because you're at 900 megahertz. But still, the wavelength is still 30 centimeters. So the dots don't have to be too close together. It's all 900 megahertz is a nice place to work. Everything sort of works as far as the length of wires and the size of resistors and so on. It's an easy way. The tags, we gave you some of our tags at one point, right?
Right. Yeah.
Those are all nice. I don't know if you are fully aware of the fact that those are 900 megahertz tags, as we gave them to you, but they're tunable from 433 to 927.
Oh, okay.
And they can be receivers. So you can actually use a tag like that. Now imagine you put a tag like that on somebody's chest and then it made a Doppler measurement. You'd probably have a much cleaner signal for heart rate.
Okay.
And
I think that probably we can also try the PIP tags.
That's what I'm talking about. The PIP tags go from 433 to 927 in 1 hertz steps, and you've got huge control over the amplitude too. So, but that's more playing with hardware, which right now, without playing with hardware, you can get breathing, and if you match it with disaster management and triage, you've almost certainly got something worth talking about.
Sounds good. Sounds very good.
Yeah, and
there are many things we can actually explore. I think it's very good we talked to you. Yeah. I have another meeting coming up at 4:00 with Cisco. So
Well, that's fine. I just wanted to make a connection, and I wanted to let you know, since I don't run into your students anymore at WinLab.
That's the thing. So actually, I would like to ask you, if you have time, for this project, okay, we just get started. We tried a little bit. So, do you want to join us? We have this bi-weekly group meeting for this project.
What time is it?
Usually it's Tuesday morning, 10 to 11.
Let me just check. Tuesday.
So not today, next Tuesday is the cycle for this.
No, I understand. Tuesday is actually pretty good time for me usually. Tuesday at 10 to 11?
Yeah, 10 to 11.
I'm happy to join.
Okay, that's great. Yeah, if you have time, I hope you can join. I think it's very helpful. You have a lot of knowledge in this, and with your physics background, that's I think it's a perfectly fit match actually experiences to explain many things behind this, so that we can try. Your suggestions. I think it's actually very valuable to us.
It's actually kind of fun because I took a medical instrumentation course at the Stanford Medical School when I was there, which was a real kick. That was a long time ago, but at least I know how all this stuff works.
That's great.
Yeah, and we also have our collaborators from NYIT. They also join us at that time, so we can.
Oh, that'd be good, right?
Yeah.
And the hard part about dealing with me is telling me when to shut up. So I leave that to you. You tend to open up things like this, and I've thought about a lot of these things, so I've got a lot of ideas.
And also I during our conversation, I'm also thinking that in addition to the text we're trying, I think we can also try the pip tags that your company has, right? So by looking at that, because for the pip tags, definitely we can adjust the resistors. So
you could definitely adjust the resistors, measure the resistance, and send that information back.
Yeah. So we have a much better control of that tag. So if we can have two sets of tags, and then we can work for this different kinds of applications, I think that will be very helpful for our research.
May I also point out that if you wanted to learn more about the heart, you could run an ultrasonic transducer off of a pip tag. And let me see if I can describe what we did with HeadFi. Was we have a transmitter here, okay? We have just a transmitter, and we send out a signal, and we look at how much power you have to put in the transmitter. If there's a reflecting area nearby, the amount of power the transmitter needs depends upon where that area is. Because if it's further away, the signal gets attenuated and it bounces back with a different phase. So that you have to put a different power into the transmitter to get the same voltage on it. So that's what Xiaoran was doing, was measuring the amount of current the transmitter took to give a constant signal out as things moved around, or your ear was in a different position.
Oh.
So you could put a pip tag on somebody's chest, have it send an ultrasonic pulse out, receive the ultrasonic pulse, and learn something about the heartbeat directly, and send that by radio back.
Oh, that's good.
Without using, it's all fairly programmed. It's all a MSP 430 processor, so it's a straightforward programming. You would have to, and it's 3 volts, so you'd have a very, very low power ultrasound, but you're only trying to detect the heart from right above the heart, so it might actually work. It's an interesting, if you wanted to get an ultrasonic transducer, hearts are so easy to detect that a small one with a few volts on it might actually work.
I see. That's good.
Does that make sense? That's way into the hardware realm where you don't normally go, but because the tag board already exists, it's a question of soldering transducers on it and writing the software, so it may not be so different.
Okay. Sounds good. Yeah, that's very good. Yeah. I have to get off now, and then...
Okay, good. That's fine. As I say, it's hard to get me to shut up.
That's very good talking to you. Such a long time. I'm actually very happy. Yeah. Sorry, I have to run to my next meeting. So
Take care.
Probably we meet again next Tuesday.
Okay, I'll put that on my calendar next Tuesday.
Okay. And Ian will send you an invite.
I will send you an invite on the Google Calendar.
Yeah.
Oh, wait a minute. Let me just, before you do that, next Tuesday actually has I may have a problem next Tuesday. Let me just check. You can go ahead.
And then you can try to work out the schedule. Yeah. We can also work. Yeah, I think you're very valuable to us. So I think we can we can also move around our schedule a little bit.
Yeah.
Rich.
I'm sure we can move it.
Sorry that I have to get off. Very nice.
Okay, good. I'll talk to you later. Bye-bye.
Talk to you later.
Yeah.
Thank you. Bye.
Thank you.
Thank you.
Yeah. Okay. I'll send you guys, if anybody else wanted to talk